Next parameter to be used is the outlet enthalpy of air. So the outlet enthalpy of air is equal to the next parameter to be considered is the outlet enthalpy of air. It is just equal to the saturation enthalpy plus the product of the L/G ratio multiplied to the difference between the hot water temperature and the cold water temperature. At the enthalpy difference table, we will consider a range which is from 80 degrees Fahrenheit to 100 degrees Fahrenheit. H prime here is just literature values obtained from the air-water vapor mixtures table. H is obtained from the equation or from the method of calculating for the outlet enthalpy of air. From the equation of outlet enthalpy of air, values such as the saturation humidity and the liquid loading to gas loading ratio as well as the hot water temperature is constant. Cold water temperature varies from 80 to 100 degrees Fahrenheit. Then we are going to subtract the literature values and the outlet enthalpy of air from 80 to 100 degrees Fahrenheit. We will average the first two differences such as 13.7 and 15.27 to get 14.485. The average of 15.27 and 17.67 is 16.47. And the average of 17.67 and 20.839 is 19.254. The average of 20.839 and 24.98 is 22.909. Then, finally, we will use our equation by numerical integration for calculating the tower characteristics or the parameter KAV over L, which is just equal to the integral form of dT or the temperature difference divided by the average difference between the H prime or our literature value minus RH or the outlet enthalpy of air obtained by calculation. So the values obtained are 0.345, 0.303, 0.259, and 0.218. And by numerical integration, we will just add these values to obtain 1.125. Thus, our KAV over L or our tower characteristic is approximately 1.1.
Now, we're going to solve the tower characteristic by using the Chebyshev method. This process of determination of cooling tower characteristic is basically equation-based calculation. The formula to be used is KAV over L is equal to the integral of dt over HW minus HA from T2 to T1, which is approximately equal to T1 minus T2 over 4 times the reciprocal of enthalpy differences at different temperature, where HW and HA are enthalpy values of air-water mixture at bulk water temperature and wet bulb temperature respectively. Delta H values are enthalpy differences at different temperature given by the following formula. T2 and T1 are cold water temperature and hot water temperature respectively. The table shows the enthalpy differences at different temperature. The enthalpy of water is obtained from steam table from Perry and enthalpy of air is obtained from tower characteristic curve. Substituting all the values to the equation presented earlier, the KAV over L value that will be obtained is 1.11.
Next, we will be solving the problems by the nomograph method, which is simply a method which utilizes the nomographs found in Perry's Chemical Engineer's Handbook. So for the problem, we're given the wet bulb temperature of 65 degrees Fahrenheit, a cooling range of 20 degrees Fahrenheit, a cold water temperature of 80 degrees Fahrenheit, and an L/G ratio of 0.8662. So for the first question, we will need to find that our characteristic that will suffice for these given conditions. So first we go to the nomograph found in Perry's Chemical Engineer's Handbook, And then we will plot the given cold water temperature and cooling range and wet bulb temperature, and then draw a line from these 3 points, which in this slide is the line in the lower part that has the red dots. And then to find the actual KAV over L or tower characteristic, we will find the point of the given L over G ratio and then create a straight line parallel to the first line, extending from the L over G line into the KAV over L line. And then the intersection of this new line into the tower characteristic line will be the value of our KAV over L, which in this case is 1.112. So, comparing the value obtained from those obtained from the Chebyshev method and the numerical differentiation method, they are almost equal with only about 0.01 difference. Now next, we are required to find the required water concentration for this cooling tower. So we will use the next nomograph found in Paris Chemical Engineer's Handbook, and then we will be plotting the points of the cold water temperature, hot water temperature, and the wet bulb temperature. And then we will connect the 3 points and then find its intersection with the water concentration curves in this nomograph. So for the given problem, the required water concentration that we will obtain will be 3 gallons per minute square feet. Then for that, now we will be using the last nomograph, which is used to obtain the horsepower requirement per square feet of tower area. So in this part, we are required to obtain the power requirement per square foot of tower area of the given cooling tower if the tower operates at 100% of the standard tower performance. So to obtain the horsepower requirement per square foot of tower area, we will just find the point of the 100% tower performance and then create a line extending from that point to the horsepower per square foot of tower area line, which passes through the turning point. So in this problem, we will obtain a horsepower requirement per square foot of tower area of 0.04 HP per square feet.